Hello and welcome to our lecture on systems of linear equations. I am actually going to combine sections 4.1 to 4.3, so that way it is one cohesive lesson on systems of linear equations. Now, looking at a system of equations, the first thing that we have to identify is a little bit of vocabulary. That way we understand what it is we're looking at and how we can really discuss the linear systems themselves. There are three possible situations whenever you're dealing with a system of linear equations, which is essentially more than one set of line that you can use within an equation, or within a system, rather. You have, in this course, two lines within your system. Now, in this particular instance, you can see I have all three situations already listed. These are also listed within your notes on your handout. However, it's a little hard to see when it's just black and white, so I'm using multiple colors within this video so that you can see the individual lines as we work through them. The first situation is if you have one solution. And if you have one solution for your system, that means you have one point of intersection, or where these 2 points meet for their intersection. That would be considered the solution itself. This is also described as consistent because you are consistent at one point between the two lines, and independent because the two lines are independent of each other otherwise, meaning they go off in their own direction, either direction, as long as they only meet at that one point. And lines cannot curve, therefore they cannot come back and meet ever again. The second possible solution set that you might get is no solution. And that is if you have parallel lines. These lines will never intersect, and therefore your solution set would always remain as zero possible solutions, or no solution. We describe this as inconsistent because you have no consistencies between the two lines, and these are still independent lines. However, because this is our only inconsistent situation, often this is referred to as just inconsistent or no solution. The last example that we have is all possible solutions. The all possible solutions is quite literally the same line in both systems. So you have one line sitting on top of the other, and they have all points shared within their solution set. This is both consistent and dependent. Consistent because you are consistent at every single point, and dependent because one line set of solutions depends on the other line's set of solutions. Okay, with that being said, for terminology out of the way, let's jump into solving some linear systems. So again, I will use multiple colors just to help us work through this problem. So I'm going to put my graph here for my system. However, I am going to utilize my other colors. That way I can show my two equations as we work through them. Okay, the first equation is x minus y is equal to 3. And the second equation, if I can write with two markers at the same time, is 2x minus y is equal to 4. Now, this particular set of instructions says solve the linear systems by graphing. And so what we're going to do is we're going to graph and determine if any of these situations apply. So which one of those situations will actually apply. So let's work with the blue equation first. I'm looking at this side. If I'm trying to graph, I need to actually use an XY chart. So I'm going to use 0 and 0, just like so. If I plug 0 in for x, it goes away. I have a negative y is equal to 3, or y is equal to negative 3. If I plug 0 in for y, x will equal 3. And I can plot those quite easily, very quickly. 0, -3 means I am down 3 units right here. 3, 0 means I am to the right 3 units right here. And I would connect those with a straight line. So there's my first equation in my system of equations. Now working with my purple line, what I'm going to do is the same thing. I need to create an XY chart so that I can get my points and then graph this system, or sorry, graph this equation. Okay, so if I plug 0 and 0 as my test points. So 0 for x means that I have a negative y is equal to 4, or y is just negative 4. If I plug 0 in for y, I have 2x equals 4, or x equals 2. Plotting these 2 points, I have 0, -4 right here, and I have 2, 0 right here. Now, as you're graphing, you notice that your points will intersect in your graph. And they intersect at approximately 1, -2. I say approximately because whenever you're solving by graphing, unless you're using a perfectly scaled graph, and you can see very clearly that these two lines are crossing at a point, what you're getting is an approximation. So the perfectly scaled system where you have a very clear, definitive crossing at a single point, that is where you can really solve by graphing easily. But when you're graphing such as this, or if you're graphing and your points appear to cross a little off of, or sorry, your lines appear to cross a little off of a regular point, or an integer point, I should say, that's when you have to say approximately. Now, in this system, you do have only one point of consistency, which means your system is both consistent and independent, meaning you have only one possible solution, or one shared point among the two lines. Okay, with that being said, let's try another problem. I do need my board space, so I'm going to erase what I've got here. We'll do one more by graphing, and then I want to show you a way of doing this a little more precisely. So again, I will get my little coordinate plane up here using my black marker. Easy to see that one, very neutral. And my two equations, I'm going to use blue and purple again. My first equation is x minus y is equal to 3. My second equation is negative x plus y equals -3. Okay. So let's go ahead and plot these by getting our XY charts. So I'm going to use my 0 and my 0 again. We've actually already solved this equation. It was the first equation in our last problem as well. But that's okay. We'll do it again since I erased it. If I plug 0 in for x, negative y equals 3, or y is equal to a -3. If I plug 0 in for y, x is positive 3. I plot these points. At 0, -3, I have my first point. 3, 0, I have my second point. And I'm going to go ahead and connect those. My next equation, I get my XY chart. I'm going to use 0 and 0 again, just get my intercept values. It's always easier that way in my opinion. If I plug in 0 for x, y is -3. If I plug in 0 for y, x will be positive 3. Now, you might have noticed already between my two XY charts, they're exactly the same. So what am I actually looking at here? I am looking at a system that has all possible solutions. And because it has all possible solutions, I can describe the system as consistent and dependent. Consistent at every point, dependent from one line to the other throughout the system. And so graphing is a very easy way to identify quickly what kind of system you're actually looking at. And so you can actually go a little bit further with this. We've talked about comparing slopes a couple units back, couple lectures back, I should say. And so when you compare the slopes of lines, this will help to give you an understanding of what it is that you're actually looking at. So I don't need two colors for this section, so I will just use my one marker. If I have a system of 2x plus y equals 0, and 2y is equal to 6 minus 4x, and without graphing, I have to decide whether these lines are identical, parallel, or intersecting at a single point. And then how many solutions does the system have? There's a lot of components to that. But the first things first, I need to get my slopes because right now my lines are all over the place in terms of equation. So I need to get slope-intercept form. That's the easiest way to compare. Solve for y in both equations. This equation goes to y equals negative 2x. This equation, I have to divide by 2. I'm going to move my 4 over here, so I'm just going to reverse these two terms. So that will give me y is equal to a negative 2x plus 3. Now, comparing my slopes, I have a slope of negative 2 for my top equation. I have a slope of negative 2 for my bottom equation. Well, gee, I have the same slope. If you think back to the lecture we talked about before, whenever you have the same slope, you can have parallel lines, meaning they are changing in the same direction. There's one small additional requirement we have to look at. Because we're looking at a system of equations, we want to make sure we're not talking about parallel lines versus the same line. And so we have to determine within our equations whether or not these are the same line. Hence, it would be the same exact equation if it were the same line. These are not the same equation, but they have the same slope. This equation is missing a plus 3. And so these lines are parallel. Now, the next question is, how many solutions does this system have? Parallel lines are two independent lines, and they have no points of consistency because they do not intersect. So there are no solutions here. So without graphing, we just did a quick analysis, if you will, of our equations and determined that there are no solutions to this problem. Very good. Let's try another one. My next system is 3x plus y equals 1 and 3x plus 2y equals 6. Okay, so we're going to do the same exact thing. We are going to solve for y in both equations to get slope-intercept form. In doing so, we're going to subtract 3x on this side. That's y is equal to a negative 3x plus 1 for the first equation. Excuse me. For that second equation, we're going to subtract 3x, but then we also have to divide by 2 to everything. And so that becomes y is equal to a negative 3 halves x plus 3. So we subtracted 3x and we divided by 2 to everything. Let's look at our slope. Our slope here is negative 3. Our slope here is negative 3 halves. Well, they're clearly not the same slope. And these two slopes are not opposite. So there's no possibility that they even could be perpendicular if we were thinking of that. Now, that being said, looking at these two lines, because they don't have the same slope, that means at some point, even though they're changing and they might be changing very close to each other, at some point they will intersect because they don't have the same slope. What does that mean for us? They will intersect at one point or at one solution, thus making them consistent and independent lines. All right, let's do one more, and then we'll go into exact analysis. Okay, so I have 6x plus 4y equals 6. I have 3y minus 3 is equal to a negative 2x. Okay, so again, we're looking to see about the analysis here. We have to solve for our slope. So what we're going to do is we're going to look at this, solve it for y. First, we have to move that 6x over. So that gives you 4y is equal to a negative 6x plus 6. You also have to divide by 4. The reason I didn't do it in the same step like I did the last one is simply because you also have to reduce. So I'm going to reduce and divide at the same time here, which means my equation will be y is equal to a negative 3 halves x plus 3 halves. This equation, I need to move this 3 over and divide by 3. So I'm going to do that all at once. So I'm going to have y is equal to a negative 2/3 x plus 1. Comparing my two slopes, I have a slope of negative 2/3. I have a slope of negative 3 halves. These are not the same slope. They're not even perpendicular lines. So what we're seeing here is that these two lines are independent and they would be consistent at one point. So there is one possible solution here. Okay, so let's go into a little bit more of an analysis. And you might have heard this technique called substitution before. And you're probably thinking back, oh no, substitution, it was terrible. Substitution is actually not very difficult at all. In fact, you've been using substitution whenever you plug in values. All you're doing now is your value is really just more of an expression that you're substituting. So what we're going to do is work through substitution. And I'm going to use multiple colors here, so that way you can easily see what is playing out where. So my two colors, I'm going to use blue and purple. My first equation here is 7x minus 2y is equal to a negative 2. My next color is purple, and that is y is equal to, I believe it is 3x before my paper dropped. Oh, there we are. Yes, y is equal to 3x. All right, and we are going to solve by substitution. Now, that being said, I'm going to try clipping my notes up here. There we go. Oh, no, that's not going to work. I'll just put them right there. If they fall over, they fall over. Now, as we're looking at this problem, the process of substitution requires you to solve for one variable and then plug that value in, whatever that expression happens to be, plug that in to the other equation. So, what are we doing here? I have 7x minus 2y is equal to negative 2. I would have to do a little manipulation to be able to solve for a variable. It's not bad, but you can do it. This one is y equals 3x. Hey, this one's already solved. Let's use it. So if y is 3x, why don't I take this value and plug it in? So let's do that. So I have 7x minus 2y. My y is 3x. Notice where I plugged this in. Is equal to a negative 2. At this point, you're in one variable equation. Solve it. So I have 7x minus 6x equals negative 2, or x is negative 2. Hey, that was pretty easy. Now, I have x, but I'm missing y. So if you ever come out to an x value like this, you must go back and solve for y, because that means your two lines will be crossing at a single point. So you must go back and solve for your y value. So here's x. I'm going to take this x value and I am going to plug it in. You can plug it into either original equation. It does not matter, but I highly suggest you plug it in to the easiest of the two equations. That way you have easier analysis. So you have y is equal to 3x. I'm going to plug in my x value. So I have y is equal to 3 times negative 2, or y is negative 6. What does this mean for you? It means your end result is actually a coordinate value. It's a location. It's like a treasure map. You have negative 2, negative 6. And that is your solution point. That is where these two lines will intersect exactly. All right. Pretty easy, right? Wasn't too bad of a process. So let's do a couple more for practice. Because that one, of course, is easy. It's the first one, right? So let's try this next problem. The next problem is 5x minus 3y is equal to a negative 6. Your second equation is x minus 2 is equal to a negative y. Oh, there we go. Equal to a negative y, just like that. Perfect. Now, again, you have to solve for a variable. It doesn't matter which equation you have to work with, but you do have a little bit of manipulation still. I'm going to solve for x in this problem, just because I can. And if you wanted to solve for y, that's fine too. You'd have to multiply a negative 1. But I'm going to solve for x by simply adding 2. So I'm going to rearrange this problem. It will be then x equals 2 minus y. Easy enough. All right, I'm going to plug this value in for x in the first equation. So I have 5x, which is going to be 2 minus y, minus 3y is equal to a negative 6. All right. At this point, I'm in a one variable equation. I'm going to start solving. Distribute here, that's going to be 10 minus 5y minus 3y is equal to a negative 6. 10 minus 8y is equal to a negative 6. Just for giggles, I'm going to move my negative 8y over here to keep it positive. I'm going to move my negative 6 at the same time. So that gives me 16 is equal to 8y, or y is equal to 2. At this stage, you have y, but you need x. If only you had an equation for x. Again, you can use your original equations, but you also manipulated one of those original equations, and you can use that as well. So if you do, just be very careful, because if you messed up your manipulation, you would have messed up your entire problem anyways. So that being said, let's plug in what we have. I have x is equal to 2 minus y, which is 2, or x is equal to 0. What does that mean for me? That means I have a point of intersection at 0, 2, just like so. Perfect. So the process of substitution is super, super easy. It's actually not scary at all. You have been doing it already throughout the course. Anytime you substitute a value or plug in a value, as you might know it, you are actually doing the process of substitution. All right, let's do another one. Let's say I have negative x plus 2y is equal to 8. And for my next equation, I have 4x minus 8y, excuse me, is equal to 1. Okay. Put my notes there, and let's tackle this. Okay, so we are going to solve by substitution here, but there is a small problem. Both equations here are not solved for a variable. That means we have to pick one of the equations and solve it, kind of like what we did on the other problem. Now, it doesn't matter which way you go. It does not matter. I'm going to just simply take this first equation and solve it for x, because that would be just my preference. Does it matter? No, but I'm going to use this one. Okay, so that being said, I'm going to simply add x over and subtract 8, which means I have 2y minus 8 is equal to x. Which then means I'm going to plug in my x value, so I have 4 times x, which is the 2y minus 8. And then I'm going to subtract my 8y and equal 1. So I'm simply plugging in my value. I am now going to do my distribution and solve, because I'm in a one variable equation. See what I get. So I have 8y minus 4 times 8 is 32, minus 8y is equal to 1. 8y and 8y cancel. I get negative 32 equals 1. How strange. Now, when does negative 32 equal 1? Never. It's never going to equal. Those are two vastly different values. That being said, what this means is that we are dealing with parallel lines that are inconsistent and independent, meaning there are no solutions. So for this particular problem, there are no solutions. Okay, cool. So substitution, some of you might find as an easier method. Some of you might find this next method easier, and others will find that it depends on the problem. And they're absolutely right. Because if you're looking for one set way of doing this, that you can just get through and do it, be done, substitution works every time, and it's a skill that will actually be reinforced throughout the course, as well as any future math courses. However, some problems are written a little bit more in line with what we call the elimination or the addition method. You've probably heard both. I believe your textbook calls it the addition method, but it's the same exact thing as elimination. So let's take a look at that. Let's look at my two equations in this system. I have 3x minus y is equal to negative 7. And I have, oh, there we are, got to get my marker. I have 2x plus y is equal to a negative 3. Now, you might be looking at this problem and say, hey, I see something. I see that my y's are here, but they have different signs. And that's exactly what you want. So when you're looking at the elimination method, what you have to do is have from your original equations or from equations that you've had to manipulate, because you may have to do a little manipulation there. What you need are one variable that is opposite in sign, but it has the same integer value. So it has the same value here, and it's opposite in sign. Perfect, we're already set up. Once that's achieved, simply add your equations together. 3x plus 2x is 5x. Negative y plus y cancels. Negative 7 plus a negative 3 is going to be negative 10. Okay. Solve that out. I get x is negative 2. Perfect. Now, once you have that value, you have to plug it back in. So you get to take the x equals negative 2 and plug it into either equation. It does not matter. Pick one to your heart's content. I'm going to use the first one. So I have 3x which is my negative 2. Plug that in. I get negative 6 minus y is equal to negative 7. Woo, negative 7. Add my 6, that's negative y is equal to a negative 1, or y is 1 once you divide out that negative. Very good. And you have a solution point of negative 2, 1. So there you are. So the elimination method can potentially be very easy, just like it was. Just like it was. However, it's sometimes not as easy. Let me show you one that takes a little manipulation. Let's do this one. It's 6x minus 2y is equal to a negative 21. I'm going to use just the one color at this point because the elimination method does not necessarily have a lot of movement in terms of the items, unlike the substitution method where you had to take one part and plug it into the other. So what we're going to do is just use the one color and jump right into this problem. My next equation is negative 3x plus 4y is equal to 36. Now, notice that I don't have an easily identified variable like the last problem that I can just right off the bat cancel. I have to do a little work. So here's what we're going to do. We're going to pick a variable. Does not matter if it's x or y. I encourage you to do both. That way you can see which one works better for you. But I'm going to pick x. I just want to cancel that. I have a 6x here. I have a negative 3x here. I need those values to be the same, but opposite in sign. So this is positive, this is negative, so I have already got that. But this is 3. To get to 6, I need to multiply this by 2. So I'm going to multiply the entire problem by 2. And I'm going to rewrite it. So my original first equation here is 6x minus 2y equals negative 21. That did not change. My second equation, once I multiply that 2, is negative 6x plus 8y is equal to 72. So I just brought my equations down. I can now add my equations together. These will cancel. This becomes 6y. Negative 21 plus 72, I'm looking at 51. We're then going to divide by 6. So y equals 51 over 6. 3 can go into both of those. So technically it's y is equal to 17 over 2. So 51 divided 3 is your 17. And you got a beautiful fraction. This is where the graphing method really doesn't help you. So you do have to use an exact measure system like the elimination or substitution methods anyway. Now, I'm going to take this value and I'm plugging it into one of the original problems. I'm actually going to choose the first one because I see that my y has a 2 on it already, which will cancel this out. So I'm going to use that first one. I have 6x minus 2y, which is 17 over 2, is equal to a negative 21. My 2's here cancel, so that's 6x minus 17 is equal to a negative 21. Add my 17 over, 6x will equal negative 4. Divide by 6, reduce it, x will equal a negative 2/3. Which means you have a point, a solution point, of negative 2/3 and 17/2. So I'd like to see you try that one with graphing because you wouldn't be able to identify those points easily. So with that being said, we're going to try another problem. We're going to stick with the elimination method for right now. Just getting my board space set. Because I believe substitution is fairly easy, but at the same time, I think the idea behind elimination, while it's easy, it does take a little manipulation. Okay, so let's try this next one. I have 2x plus 3y equals 19. I have 3x minus 7y is equal to a negative 6. Okay, that being said, let's pick a variable, does not matter, and then we're going to eliminate it. So let's pick x again, why not? I have a 2 and I have a 3, so that means I'm going to have to multiply this whole problem up here by 3 to go to 6. I'm going to have to multiply this problem by 2, but these are currently both positive, so this will be a negative 2. First problem, 3 times 2 is 6x. 3 times 3 is 9y. Excuse me. 3 times 19, I'm looking at 57. And then if I'm looking at this next problem, negative 2 and 3x is a negative 6x, positive 14y, and a positive 12. At this point, I can combine my terms. My x's will cancel. I have 9y and 14y. Combined is 23y. 57 and 12 is 69. Divide by 23 to each of these, and y will equal 3. Now, let's take y and let's plug it right back in. So what we're going to do is pick an equation, doesn't matter which of the original equations to use, and then we're going to plug in. So I'm going to take the first one, just because. So I have 2x plus 3 times 3 is equal to 19. 2x plus 9 equals 19, or 2x will equal 10, which means x will equal 5, thus giving you a point of 5, 3. Let's do one more, and then I have a challenge problem for you. So this last problem before the challenge is 2x plus y is equal to 6. Negative 8x minus 4y is equal to a negative 24. Using the elimination method, again, you have to pick a variable that you want to eliminate. I'm going to say let's eliminate y this time. Doesn't matter, but I see that this is positive, this is negative, this is a 1, which means less manipulation. So I'm going to use this first equation, multiply it by 4, because I need to get this y to cancel out. That means I'm going to have 8x plus 4y is equal to 24 for the first equation. The second equation is negative 8x minus 4y is equal to a negative 24. I'm then going to add my terms together. And notice my x's cancel, my y's cancel, and my final term cancels. So my constant value. So I get 0 equals 0. When does 0 equal 0? Always, which means this is all solutions. This is a system where you have one line on top of the other. It's consistent and dependent. Very good. So this is all solutions. All right. Let's jump to that challenge problem, shall we? The challenge problem looks really scary. And it's really not. So get my board space again. Got to have the grand illusion of a very challenging problem here. Negative x minus y over 2 is equal to 5 over 2. I can already hear you cringing. Fractions. The second equation is x over 6 minus y over 2 is equal to 0. All right, now be honest. How many of you are cringing? Just raise your hand. I still can't see you, but that's okay. Fractions. Fractions are friends. Remember, fractions are always friends. And if you don't like your friends, what do? You eliminate them. No, just kidding about the friends, but you are going to eliminate your fractions here. So that being said, disclaimer, don't eliminate your friends. Eliminate fractions instead. This message brought to you by. Okay, so anyway, we're going to eliminate our fractions here. I see I have a common denominator of 2 in this first problem, so I'm going to multiply everything here by 2 to start with. Just see what I get. And I'm going to take my LCD here, which is 6, multiply that, and see what I get. All right, let's do this first problem. I'm going to go this way with it, so it's a little easier to keep the flow together. So that's a negative 2x minus y is equal to 5. No more fractions. This one, I get x minus 3y is equal to 0. Okay, that seems pretty reasonable. Now at this point, you can choose either elimination or substitution, and that's really a matter of preference. I personally will see this part right here, x minus 3y equals 0, as a very easy way to go into substitution. I simply have to change this problem so that it's x is equal to 3y. And then I can just plug it in. So that's what I'm going to do. So I have negative 2 times my x, which is actually 3y, minus y is equal to 5. This is negative 6y minus y is equal to 5. Negative 7y is equal to 5, or y is equal to a negative 5/7. And there you go. Now, from here, you could easily plug into an original equation. And you'd be like, oh no, fractions with fractions, ah! It's okay. It's very simple. You already manipulated a problem that's solved for x. Plug it in. So you have x is equal to 3y, which is negative 5/7. Or x is equal to a negative 15/7. Much easier than what you thought, huh? That means your end point here, your point of intersection, is going to be a negative 15/7 and negative 5/7. And there you are. Okay, guys, this concludes our lecture on systems of equations. I will be starting another lecture here in just a few moments.